Absolutely. So basically, in a typical weather prediction model, and same goes for an ocean prediction model. You saw what we call a system of primitive equations, and that's basically a subset of, or really an extension of Navier-Stokes equations. So you have an equation for momentum conservation, mass conservation, and then on the atmosphere side, you solve for thermodynamics.
Welcome to a new episode of the Engineered Mind podcast. I'm your host Yusef, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I am very honored to welcome Milan Curcic to my show. He's a scientist, founder and author of the book Modern Fortran. He studies ocean waves in the Sustain Lab at the University of Miami using theory, experimentation and numerical modeling. His expertise is in wave physics and numerical weather prediction. In this podcast, Milan and I talked about weather prediction models and how they differ from the classical CFD approach, the fundamental flaws of today's weather prediction models and how they can be optimized. We talk about the butterfly effect and chaos theory. We talk about Cloudrun, an on-demand SaaS platform for custom numerical weather prediction modeling. And last but not least, we cover Fortran, its origin, and how to combine it with machine learning. And now, ladies and gentlemen, here's my podcast with Milan Curcic. Hey Milan, welcome to my show.
Hey Yusef, thanks so much for having me.
This is so great to have a Fortran expert today on the show. So we never talked about Fortran on the podcast, so today is the day. But before we jump into the beautiful aspect of Fortran and where we can use it, and maybe you can give us like a 1 or 2 minute bio. Who is Milan and how does your background look like?
All right, so I'm a scientist, meteorologist, and oceanographer. And meteorologist does not mean a TV weatherman, basically atmospheric scientist and also ocean science. So atmosphere and ocean are very connected, close to each other. So not only physically, but in terms of the science behind them. Basically, you can explain them with the similar kind of equations, except the atmosphere has clouds and humidity and rain, whereas ocean has salinity. So they're a little bit different in that sense, and they're the surface at which they connect. You have waves, as you know, those are important for exchange between atmosphere and ocean. They're also very important for surf. That was, when I was, say, high school to college kind of time, still in Serbia, where I grew up and went to school for my undergrad. I was watching a lot of surfing on TV, and Serbia is a landlocked country. Even though we went to to the Mediterranean for vacation, I never got to experience like open ocean and swell and surf. So that was always kind of like a fantasy for me, and that's in a way what brought me to grad school, to Miami, the University of Miami. I came in 2009. So I graduated with a degree in meteorology, and I always wanted to do something more with the ocean. So I applied to a joint program, and that's where I got my PhD, stayed for a few years as a postdoc, moved around a little bit, but now I'm for 3 years now, I've been back at University of Miami. Now I'm an assistant scientist there in a lab called Sustain laboratory that has its main feature is a big wind wave tank, and it's the largest wind wave tank in the world that can generate Category 5 hurricane force winds and stronger, and also to mechanically generate waves. And what's important about that is that we can put instruments in a controlled setting in the tank and set up any kind of condition that we want to study, which is very difficult to do in the field. And there's a lot of field work and aircraft reconnaissance when there are real hurricanes approaching land, but hurricanes are very transient and they're moving and they're very destructive. So it's very difficult to put out instruments in the field because they get destroyed. It's very expensive. So our lab is kind of a perfect setting for studying fundamental physical processes about waves and air-sea exchange in hurricanes. Is that a good summary, do you think?
That's a good summary, yes. And also when we talk about weather prediction, like meteorology, does it fall under the category of computational fluid dynamics, short CFD? Is it something similar? Is it similar?
Absolutely. So basically, in a typical weather prediction model, and same goes for an ocean prediction model, you saw what we call a system of primitive equations. And that's basically a subset of, or really an extension of Navier-Stokes equation. So you have an equation for momentum conservation, mass conservation, and then on the atmosphere side, you solve for thermodynamics, for condensation. So basically, how does humidity and temperature lead to generation of rain droplets? How do rain droplets going to rain when rain falls out? How does that affect the thermodynamics? So it's a bit of an extended system of Navier-Stokes equations. And one important difference in weather prediction models relative to more classical CFD is that there are many processes that are unresolved on the grid. So there are several, or maybe even up to a dozen, subgrid scale parameterization schemes. So you can think of them as smaller, typically 1D empirical models that run either on each grid or on the column. So a typical could be when you have, say, convective clouds, and you can't really resolve, the physical process that drives the generation of clouds and rain droplets and all that. You need to have, strong updraft, vertical motion going up in the atmosphere. And with grids that we can typically resolve for weather prediction models nowadays, that's about 1 kilometer size grid cell. Mm-hmm. So that's more typical for regional models if you're solving only for, say, Europe or US. And for global, maybe it's more typical is about 10 kilometers. So now if you imagine a grid cell of 10 kilometers, that's, you get one value of the velocity, mass, temperature, humidity, pressure for a 10 by 10 kilometer cell. So, and, if you look out, typical clouds are, they can be bigger than that, but often they're smaller. So they're unresolved in the model. So then we have an empirical model, what we call a parameterization scheme, that solves for the contribution of unresolved clouds on the grid resolved parameters like UV, W, temperature, humidity, pressure, and so on.
Wow, that's so interesting. So when we talk about 10 by 10 kilometer grid, like that sounds huge. For example, when you start doing computational fluid dynamics in university, for example, you have a few millimeters or a few centimeters of a grid, and now you have like 10 by 10 kilometers. What about the turbulence model? Is it something that we know from uni? You include maybe large eddy simulations in your weather prediction, or is it like a special kind of turbulence modeling?
Yeah, there's definitely, so for more specialty applications, when you go to finer, what we call them basically LES scale. So when you get down to about, say, 100 meters, a lot of people use, so the key is to turn off a more crude empirical model that resolves the mixing and the turbulence in the boundary layer, and to use, say, an LES. And then that's still far from getting down to, DNS kind of scale. There's people and groups who do that kind of modeling for atmosphere and ocean applications, but that's very specialized. So yeah, there are models where you can enable an LES kind of mixing in the boundary layer as a model switch.
Mm-hmm. I can imagine that this is like a super complicated and incredibly fascinating topic. So before we jump into the implementation, then we talk about programming languages. I think a lot of people ask themselves when they watch TV and the weather news, they'll be like, okay, they say tomorrow it's sunny, but then suddenly it's cloudy. They're like, okay, why do we even have weather models? Well, we have a model, and all models are wrong, but some are useful. How good do you think these weather predictions are, in fact, and can we do better? And where do you see it going maybe in 10 years, 15 years, especially now with the rise of faster computers?
Yeah, so short answer, in my opinion, I think we can definitely do better, and we are improving year over year. So with these kind of models and really any nonlinear chaotic system, so turbulence, and atmosphere has turbulence in it, ocean has turbulence in it. It's a nonlinear and chaotic system. So what we mean by chaotic is that a small perturbation or error in the initial condition grows fast because of the nonlinearities in the equation. So, for example, in the Navier-Stokes, the advection term is, say, in simplest terms, u nabla u, right? And so u multiplies the gradient of itself. So that's a nonlinear term because it's basically it multiplies itself. So in that kind of system, small errors grow very fast, and that's why we have, you could say it's arguably a fundamental limit in weather predictability. By weather predictability, I mean how far and how well can you predict weather, the ability to predict weather. And any kind of nonlinear system like that, basically errors come from two things: initial conditions. So if you have a perfect initial state of the atmosphere, then you also need a perfect model. So you need a complete, detailed, and exact representation of the system in your mathematics, in your numerical implementation, and so on. So now you see there's two problems. There's problem in the initial conditions. We can't possibly know the exact initial state of the atmosphere. And by initial state, I mean the time at which you initialize your simulation and then onwards. So we call it, say, time zero. Mm-hmm. So we can't possibly know initial conditions perfectly. Even if we had full coverage, and we don't. Okay, to speak a little about coverage. So we have a lot of ground weather stations over land, more so in the western hemisphere than in the eastern hemisphere, more so in the northern hemisphere than in the southern hemisphere. That's just because of global economics. And then we have more data on land than we have over the ocean. It's very difficult to put and maintain stations over the ocean. We do have some buoys that are well maintained, but they're very scarce relative to land measurements. Now, what helped a lot starting late 60s, 70s are observations from space, from satellites. So now, because polar orbiting satellites, they go very fast, they make their orbits fast. They do, I believe, several orbits per day. You can get pretty good global coverage, but with a lot of holes in between. So now you're kind of starting to fill the gaps over the ocean, over southern hemisphere, and so on. But we are still far from full coverage. And another challenge is, even if you have so many satellites to cover the full globe, there's still challenges in resolving the vertical distribution of properties in the atmosphere. So we don't worry only about what's happening at the surface. We need to know what's happening in the full troposphere. So that's at least, the lower 10 kilometers of the atmosphere, and I'd say even 15 or 20 are important. So we are still far from having even decent initial conditions for weather prediction models. So that's one. And another is imperfect models. Mm. We have, like I said earlier, we have coarse grids. We have a lot of processes that are unresolved on those grids. And we fill those gaps with imperfect empirical parameterization models. So you have initial condition errors, you have model errors, and combining the two, your errors in your simulation grow to a point where the quality of your forecast cannot be distinguished from just looking at a climatology. By climatology, I mean past archives of data. So what's today? Today is September 16. your weather forecast error is saturated if you don't get any useful information beyond looking at, what was the weather like September 16 last year or the year before that, or averaged over the past 50 years. That's what we mean by climatology. So once you reach, basically it's kind of like an S-curve, how your error grows. Starts slow, then grows, and then it tapers off to basically a climatological error at which you don't have any more useful information.
I see. It's also beautiful that you mentioned this with the initial conditions, which is like there's this analogy with the butterfly effect, right? That a butterfly, like the moving the wings of a butterfly in one country or one place could cause a tornado in another place. So it's really, yeah.
That's exactly right. So I believe that analogy actually came from the same guy who discovered chaos in nonlinear systems, Ad Lorenz. He was a meteorologist, I believe, at MIT in the 60s, 70s. So he's a quite important historical figure for meteorology because of his discovery.
Yeah,
and people will find this interesting. He discovered it kind of by accident. He was running his simulations, and at some point, so we write what we call restart files every day or so. Basically, it's a snapshot of the full model, basically a snapshot of your model on data, on disk. So you store it so that if your simulation crashes for some reason, like power goes out, then you can go back to that snapshot and you can restart it. And you should be able to restart it in a bit-to-bit reproducible way. If you continue from that file and you redo the simulation, they should be exactly the same. Well, what he found was that his simulations they were different every time he would restart it. And he found that it had to do with the limit, like the precision limit to which he was storing his data, which led him to a conclusion in finding that, these small, round of errors would every time build up to, basically through chaos, to a completely different state in his simulation. And that led to what we now understand as chaos.
Yeah, that's beautiful that you mentioned this, because these round-off errors bring us to the numerical aspect. Well, of course, humans can kind of predict when they spill out a bottle how the water would move. But of course, if you go to large scale like climate modeling, you need computers doing these calculations. So that brings us to programming, and actually efficiently programming on large systems. So you also were involved in something called Cloudrun, which is like a SaaS application for weather prediction. Could you walk us through, maybe give us an idea of how much calculation power is actually needed to run a weather prediction?
Okay. So Cloudrun is basically a SaaS for WRF, SaaS being software as a service, and WRF being the weather research and forecasting model. So it spells WRF, but we don't pronounce it WRF, we pronounce it WRF, like Fisherman's Wharf. Anyhow, so WRF is it's open source. Actually, it's a public domain software. It's developed by NCAR. NCAR is a National Center for Atmospheric Research, funded by NSF. It's been, I believe it was initially developed sometime in the late 90s, maybe early 2000. It has evolved from previous iteration of other models. But basically, it's the most widely used open source weather prediction model. So, most people who run, weather prediction for the research, if they're not part of some, national lab, like, Navy has their own models, NOAA has their own models that they run in prediction, but usually university teams, industry often run WRF because that's kind of the most widely used, most robust, most mature. It has many features, many parameterization schemes, many contributors. It's maybe the analogy, say, for machine learning crowd, WRF is the TensorFlow of atmospheric modeling.
Mm-hmm.
So during my PhD studies, and also onward since, I was working a lot with WRF, and I was extending it, and I was coupling WRF to an ocean model and a wave model. Coupling means, when you take separate models and they're originally designed to run on their own, but you want to say, when you want to solve for the ocean as well, and you want to pass information between atmosphere and ocean. For example, winds from the atmosphere push the ocean and drive ocean currents. So ocean should respond to the wind from the atmosphere. And likewise, when you have a hurricane passing through and that stirs a lot of water and you get ocean cooling at the surface, atmosphere should be able to feel that colder water coming up. And to accomplish that coupled system, we need to connect the two models and make them run together. So basically, they're in practice on a computer, they're running side by side, but they're each making one step at a time.
Mm-hmm.
And then at each step, they're also talking to each other. So basically, exchanging typically 2D arrays, sometimes 3D arrays. So you just kind of, you program that stuff, you make it a single application, and then you run it.
Mm-hmm. Is that what we would call a co-simulation then?
I guess I never heard the term co-simulation, but I guess that's just different fields.
Yeah, probably engineering field,
okay.
Mechanical engineering.
Got it. Okay, I guess like co-simulation.
Mm-hmm.
So I work a lot with WRF, and WRF is even though it's mature and well-developed and well-used software, it's still, for the user, it's very low level. Like, you do a lot of, command line scripting, you edit configuration files, they're just plain text files. You do a lot of stuff in the terminal. It's very tedious. It's very time consuming. And because it's very atmospheric science specific, it's not user friendly. So somebody coming in from another discipline would have a very difficult time learning the system, getting it to run. Typically from me talking to people, it takes 3 to 6 months for an average, say, PhD student or a postdoc to pick up the whole system and kind of learn their way on how to run it. So, 3 to 6 months is very difficult time. Very long time for somebody to be learning this stuff. And even though there is comprehensive documentation, it's very expert oriented. So there's relatively a lack of tutorials, blog posts like you would have for Keras or TensorFlow or PyTorch, things like that, where you can just Google stuff, because so many people are doing it. People are writing about it, writing tutorials, giving online tutorials, say on YouTube or at conferences. So there's a lot of resources. So that wasn't the case at all with WRF. So people who would want to learn it from the start, they would struggle a lot. And it was the same with me. But as you know, you kind of have infinite time in your PhD to do this kind of stuff. So eventually you learn, you work a lot, you develop expertise. So, and a lot of people struggled in the same way that I did. And so those are kind of basically need for expertise. And two, what I didn't mention yet, these models run on very large computers. So you need many, many CPUs to run any kind of useful production grade simulation. Just like in high-end CFD. You can't really run it on your laptop. So these are, in retrospect, what are the two key problems that Cloudrun aimed to solve. However, I did not, in retrospect, I did not identify these problems and said, okay, I'm going to solve this problem by making Cloudrun. It was more kind of like an accidental stumble upon. The story is kind of maybe silly, maybe funny. I just, in 2016, I was kind of, I was tired and kind of lonely in academia and the research world, and you spend a lot of time just like working on your problem. Sometimes you collaborate, but it's very, for me at least, it was, very low level. So I would often feel like I was kind of spending long periods of time in a cave, isolated from everybody else, because I was solving my science problems, and often it can be discouraging. Academia publishing is very, very important. I struggled with publishing for a long time, even though I did publish, and objectively looking, I have a lot of, I ended up collaborating with many people in the end. But there was a time, and especially during my PhD, when I was kind of feeling alone in my own, science topic, and we had a group, but and we interacted, but it wasn't really collaborative, to say. So I did look for a while into maybe transitioning to industry, and a lot of people are writing online about transition from academia to industry, and it's generally, it can be very daunting, and especially when you read people say, oh, once you leave academia, it's very difficult to go back. At the same time, I loved and still love the kind of the personal freedom that academia gives you. It's kind of, you have as long as you have money, like as long as you have funding to do your project, you kind of have freedom how you want to do it, pending any collaborators that you have on the project, or your supervisor. But in general, most people, they don't care when you work. They don't care how you work. They don't look if you're, showing up. Again, most people, there are exceptions. But for me, research in academia has this very nice lifestyle aspect that, I enjoy and I don't want to give up. And at the same time, it was difficult to not notice how underpaid professional academic scientists are. Say, in the US, coming out of a PhD, you get a postdoc, maybe your salary is about the same or even lower than entry level, software developer just coming out of college or even high school, and that can be discouraging as well. So for me personally in life, there's pros and cons to these things, but during that time, I did yearn for something more. And I don't mean having more things, but more like doing more things, kind of doing more different things. So I was reading forums. I started reading. I found out about this Hacker News forum. Basically, it's like a Twitter board. Sorry, not Twitter board. A Reddit-like board for tech and startups. Blah blah blah. I was reading there, and then somebody there launched their little side product or little startup. It was called Deploy, dply.co. It's not, I don't think it exists anymore, but basically it's they would offer you a single click button to launch a cloud instance for free, and you get a free cloud instance for an hour. And then if you want to extend it, you have to pay money. And that was the first time I tried a cloud instance. And up to that point, for a few years, I was reading a lot about it, but I had no idea what it's like in practice and what are all the things that it can be used for. So when I tried that, I realized, hey, I'm actually in the same kind of interface, same kind of, I'm in an Ubuntu shell, and there's all these tools that I can install and download, and let me try to compile this Fortran program, this C program. Oh, it compiles and runs. This is interesting. And this is a computer sitting somewhere far away. It's not even here. And I'm not even paying for this. Sure, it's going to expire in an hour. I think main idea or selling point was to give an easy access for developers to showcase, to demo their product or their open source project, whatever, without users having to pay for a cloud instance or having to run something on their own computer. Anyhow, this kind of put a seed in my head. Hey, so I can actually call a server, like just spin it up out of nothing, and do something. I mean, at that point, I even like downloaded the WRF and like compiled it and ran it, and it ran, and I was like, wow, this is it for me. It was kind of mind blowing. Even though at the time, so this was late 2016. At the time, there were, in retrospect, I discovered there were few other teams, fewer people exploring this kind of stuff. So I looked up, cloud providers, and I looked, AWS was very intimidating with all the options and stuff. And it was similar with Google Cloud Platform. That was seemed a little bit easier, but still, to me, it was daunting, like how many options there were. Like, it wasn't clear to me, hey, how do I just get a server with these kinds of specs, like CPU, RAM, blah, blah, blah. But then there was this provider called DigitalOcean that basically made it very simple and straightforward. And I think at the time they were advertising themselves as like developer friendly cloud provider. And they were relatively small, really good support. That's what I liked about them. So I started experimenting on there. At the same time, I was talking on the phone with my friend and old roommate Josh, and I was telling him about this thing I was experimenting in, and so what if we could make it easy for people to run WRF without necessarily having expertise to run all the shell commands and edit the files themselves, and without access to high performance computing. I myself in my PhD was very lucky that my supervisor always had a small cluster just for the lab. So even though we used university resources, which was always a larger supercomputer, we always had our own, it was in the same building, but on the floor downstairs, our own, like usually 100 to 100 core small cluster. There were no queues, no other users bogging down the system. So it was very easy to run. But actually most people in academia, so most people like me, I don't think they have that kind of luxury. Usually they have to go either to a national lab supercomputer and waiting queues, apply for CPU allocations, things like that. So there's a lot of bureaucracy and just administrative friction associated with that. So we thought, like, could we make running WRF very easy for people and without them having to have their own computer? And Josh thought it was a great idea. And he said, I was just kind of telling my ideas to Josh, but Josh said, oh, is this something I could help you with? And I was like, oh my God, I never thought about this, but we could work on this together. And so we did. So neither of us were interested in leaving our full-time jobs, which, we enjoyed them for different reasons. I really cared about my lifestyle and, the personal freedom that academic setting gives you. But we started working on this, evenings and weekends, and we launched it in early 2018. Initially, we designed it as kind of basically an abstraction of WRF, but for an expert user like me. And that was a mistake because people like me, they were in academia, and in academia, the funding cycles are very slow and tedious. Usually, you have a project 3 to 5 years. You need to apply apply for grants, you write proposal. In the proposals, you need to write how much money you're going to spend on computing. At the time, and probably still, funding agencies weren't excited to pay for commercial cloud providers when there were all these subsidized supercomputer centers that were designed and made for people like that to do research on. So it was very difficult to get people to pay for a service like that, even though everybody told us, "Oh man, this is so cool and exciting, and for WRF it's groundbreaking." But when it came to paying money for it, nobody was ready to commit and start using it. And so we also announced it on when we launched. We announced on Hacker News, and there was a really warm and overwhelming response. Sometimes it's not the case. You often see comments like, "Oh, like why would you make this?" or like, "What is this even for?" But to my pleasant surprise, it was very, very nice response, and a lot of people asked good questions and wished us well. But an interesting thing is we started getting feedback and a lot of questions from like recreational outdoor sports people. So hiking, mountain climbing expeditions, later sailboat racing, and so all of these people from these kind of outdoor sports industries, they care a lot about weather, but they don't have the weather modeling expertise that they would need to so our interface at the time, you still needed to kind of put in some parameters, even though the WRF was already compiled and set up in the cloud, ready to run. So when you'd run it, it would spit out output files and you would be able to download them from the browser immediately. But for these people who weren't experts, that was, they couldn't get anything useful out of it. So they started pushing us toward, really simplifying the interface and making data in an as accessible form as possible. So one of our early adopters, Chris Bedford, he's a weather coach for high-end sailboat racers. So he's an ex sailboat racer himself as well, but he has coached many like national teams, Olympic teams around the world. And so he was our early adopter, and he gave us a lot of good guidance on like how to make this product accessible for sailboat racers, which ended up being our main target audience, which is not something that I didn't even know about sailboat racers when we started it, when we launched it. So for me, that was a kind of a big takeaway, that often we make something and we think we're making it, sometimes we're making things for our own curiosity or to solve our own problem, but we don't realize how is it useful to other people who could use it for some completely different application.
Mm-hmm. That was a long story, no, Milan. That was a long story. I really appreciated that you share all of this with us. Very, very interesting, especially like how the SaaS world looked like back in 2018. It wasn't too long ago. But one thing I think we forgot to mention is that Cloudrun was basically based on around 1 million lines of open source Fortran code, right? And the question now is that people might ask is, why Fortran? Why not any other language?
Okay. So yes, you mentioned 1 million lines of Fortran. So that's specifically, we're talking about WRF. So WRF is implemented in Fortran. Mm-hmm. Maybe a few % of it is in C, but it's a big Fortran application. And why Fortran? So Fortran is the oldest high-level programming language. So it started in the late 50s at IBM, invented by John Backus. And so it has influenced basically all high-level programming languages that followed after. So Lisp came soon after, Algol came soon after, C came a little later, and then you have all these like languages branching out as we go toward today. Now, despite being old, and for unfortunately, most people associate Fortran with something very old, outdated, ancient history. So there's a lot of stigma and myths about it. But most people also don't know that Fortran kept evolving throughout all these years, and it has been an international standard since I believe either late 70s or early 80s. Both an international standard ISO and an American standard. A standard helps give large businesses and assurances that the language is certified and guaranteed to be performing for certain use. So I believe to businesses it gives certain sense of security. Now, Fortran evolves. It has evolved in paradigms. It's remained because of its long legacy and many mature compilers that have evolved over time. It remains the dominant language to use in scientific and engineering applications beside C++, maybe C. But it also has a large share on most supercomputers in terms of CPU hours that are spent. And over time, it has evolved in several programming paradigms. So it started as a purely imperative language, and soon I believe in its next iteration, you could do functions, so it became procedural. Later in the 90s, it became also you could do object-oriented programming, and as of Fortran 2008, which is the next to the most recent standard, parallel programming is part of Fortran syntax. So you don't need to reach for MPI, which is a library, to do your parallel computing, but you have syntax elements to express parallel programs that can be either on a shared memory system, like a multi-core laptop, or it can be on a distributed memory system, like a supercomputer. Or you can even, you can run it in the cloud. You can run parallel programs on servers around the world. It doesn't matter. And again, it's part of the language syntax. And now with Fortran 2018, it has even more features like teams, events, collective subroutines to express parallel algorithms. So I think as a language, Fortran's main selling point. It's also because of its long legacy in mature compilers, it's very efficient. So it's very easy for a novice to write math in Fortran like they would write it, say, on a blackboard. It's very intuitive. And the resulting program would be very efficient out of the box, even for a novice programmer, which is not necessarily the case with languages, say, like Python and Julia, which serve a bit different use cases, and they are generally more flexible, more powerful. But to make really well-performing programs, you really need to kind of almost master the language to do that, which is not the case with Fortran. Mm-hmm. Even novice Fortran programmers get to very performant programs very fast, and I guess that's why it's still dominant in the science and engineering disciplines, because scientists they want to solve they don't want to care about software development. They want to solve their problem as soon as they can and move on. So Fortran suits that need very well.
Yeah, thanks for the background, Milan. And also, I think you kind of contributed to this renaissance of Fortran by writing a book called Modern Fortran. So I think the audience is interested in what can they expect from your book and why should they get... Yeah, looks beautiful. I like it.
Thanks so much.
Why should they get the book in the first place?
So the book is basically a beginner's book. If you're an advanced Fortran programmer, you'll probably still get something useful out of it. You'll probably have fun with it because there's a lot of practical, hands-on examples to work through, but it's really geared toward beginners. Ideally, you should know what the variables are. You should know what functions are, maybe what for loops are or if blocks. But beyond that, you don't really need to know anything more. You don't need to know anything about Fortran. And really, you should learn Fortran and get this book if you like to learn through by practicing through interesting real-world hands-on examples. And if you know that you or think that you need Fortran for your work. So if you need very high performance or parallel code that you can write relatively easily with no need for like high expertise, Fortran is the language for you. And Fortran has indeed, it has suffered in the past 20 or 30 years. Basically, Fortran has not caught up with the developments that other languages have had in the internet era. So what came with basically internet, with forums, with exchanging code on networks, with GitHub, with GitHub repositories, people sharing their open source code. Fortran has for a long time stayed kind of in their own like little research and academic bubbles, and it has not managed up to recently to gain momentum in terms of open source communities and open source collaboration on modern tooling for Fortran. So even though Fortran was always good with mature compilers, there are about a dozen either open source or free or commercial compilers. Most of them are really good. But in general, for example, Fortran doesn't really have a comprehensive standard library like, say, Python or Go or Rust have. Fortran doesn't have an easy way, or hasn't had until recently, an easy way to package your code, to distribute it, to import dependencies, other packages as dependencies to your project, like what you would do with Conda or pip for Python. So basically, I was during the writing of my book, like none of this was still out, and one of the reviewers of my book was Andrei Chertik. Andrei Chertik is a scientist now at Los Alamos National Lab. So I've known of Andrei for a long time, even maybe from 10 years ago, from some computational science forums. I would see him answer questions. And Andrei is also known of, so if you or your listeners are familiar with SymPy, so Python package for symbolic mathematical computing, Andrei is the original creator of SymPy. And then that was from like mid 2000s, and it has evolved into a very large community open source project. So he was one of the reviewers, and at some point during the review process, we had a few email exchanges. He was very helpful with the book. At a similar time, he joined the Fortran Standards Committee with the goal to sort of accelerate and make the process, the Standards Committee process, more open, more transparent, to get more input from the broader community. Because they have worked for a long time, very isolated. Basically, it will be a collection of compiler vendors and a few other Fortran experts from the industry or academia, and they would basically work on language revisions, but with limited interaction with the community. So Andre joined the committee. On Twitter, he invited me and a few others to join to submit feedback. He has started a GitHub repository for users to submit proposals for the language, to submit ideas. Hey, this is, let's add this, or this is not good, how can we improve it, and so on. I started participating there, and a lot of people have it. There was a huge momentum. All of a sudden, there were all these people coming out of the woodwork, coming together to discuss Fortran, write proposals, discuss ideas, and that was really great. And that's still going on. But what occurred to me during reading all the requests and issues, a lot of requests were requests for like specific functions, like features that could be implemented as something that you'd find in a standard library. So there was this kind of a pattern where a lot of requests were like for things that, hey, this could be part of a standard library, but there's not any. So I suggested, why don't we start a standard library, kind of an unofficial sort of community developed and approved standard library for Fortran. And Andre was very encouraging, and he supported me. So we together started this what we called at that time Fortran-lang organization. Lang because nowadays it's cool to just append a suffix lang to any language. Say when you buy a website domain for it. I have coincidentally, for years, both Andre and I and many other people have known that these things have been missing, and that like eventually somebody's going to have to do something. Like coincidentally, I have a year before that purchased a Fortran-lang.org domain, and like just had it sit there. Even I knew that eventually somebody's going to do something with it. I just didn't know when and how or who. So just sitting there, I opened a Fortran-lang GitHub organization at the time, and like it was just empty for a year. And then when Andre encouraged me to start a standard library, then we put it under Fortran-lang. And then a few months later, ideas, or maybe even actually a few weeks later, in discussing the standard library and putting code in the documentation, there came ideas about the Fortran package manager and build system. So we started working on something we call FPM, Fortran package manager. That's something very similar to Rust's cargo. So it's Fortran specific. It's both a build system and a package manager. And it does everything for you. It has same defaults, but you can override any behavior with a specific setting. And now there's already, I believe, over 150 FPM packages. It's only been developed for about a year and a half now. And actually, an interesting fact is that FPM is a pure Fortran project, which is kind of we're all proud of it. People say, "Oh, Fortran is good for science and engineering, like simulation, but not anything else." But FPM is really a sort of a user and kind of a systems programming kind of application implementing pure Fortran. So we're really proud of that as kind of a case study for Fortran. And then a few months later, after starting FPM, we made a website for Fortran. So if you go to fortran-lang.org, you will be able to see all kinds of resources about Fortran, what Fortran is. There are tutorials, there's a list of compilers, community projects, basically everything that you want to know about Fortran today. And of course, how to contribute, how to join the standards committee. The standards committee is always looking for new members. So if you want to help, let me know. You can email me, and I'll help you get started. And likewise for all other members of the Fortran-lang community, like everybody's very helpful and very receiving to people asking for help and guidance, how to get started with this or that, how to contribute. So we need all the help we can get, and we're having a lot of fun doing it.
Perfect. And I think I will put all the links, especially to your book, where you can get a 40% discount on Milan's book, Modern Fortran, with a special code for all podcast listeners. So make sure to check it out if you're interested into Fortran. I will certainly get it. And maybe to close the podcast with a last question, can we use Fortran for machine learning?
Excellent question. Okay, so traditionally Fortran has not been used much for machine learning. I believe originally it was like mostly Lisp and C, C++. Nowadays it's a lot of Python on the high level interfaces. There were a few probably research projects doing some neural nets in Fortran, but nothing like, there's no big, or there hasn't been a go-to Fortran framework for machine learning. Mostly just like more basic statistics. During the writing of my book, actually for one of the chapters, I started, I read, I was always interested to an extent in machine learning, and I started reading Michael Nielsen's ebook on, I think it's called Deep Learning, Neural Networks and Deep Learning, something like that. So I thought, maybe it could be interesting to implement this in Fortran for one of the chapters in the book as a case study. And I did that. And then the chapter was like a monster. It was a 60-page thing because I had to explain both Fortran concepts and also, there's all this like neural network stuff that you have to explain. So the editor was like, no, you gotta rewrite this chapter from scratch. This is too much. So anyhow, what came out of the chapter was a package that I called Neural Fortran. It didn't end up in the book, but what I find fascinating is that after I released it, and a few months later, an editor of a Fortran journal asked me to write a short paper about it. So I wrote a short paper about it. That was early 2019. And what I found fascinating is that from there on, like every week, I would get like 2 or 3 emails from people asking questions about it and like trying to use it. And that has never happened to me with any other projects, even though I had a few open source projects I put out and people are using it, but it was never this much of a response. And then like several months later, I started seeing papers, kind of like physics and like chemistry papers coming out that use Neural Fortran for this stuff. And I'm like, wait, people want to use Fortran for machine learning. This is very interesting. And there's already like, there's Keras, there's TensorFlow. Why don't people use that? Well, it turns out there's a lot of people that love Fortran. Actually, we often like to say, I'm using this or that tool because of these rational reasons and these technical advantages that it has. And it does, tools do have technical advantages, but often we make decisions based on what we really enjoy and what we like. I use a lot of Python nowadays. I do JavaScript. I'm learning Rust. I always do Fortran, and Fortran always gives me the most pleasure programming. Even though, many things, Python is much easier to do certain things, certain high-level things, or if I need to do something on the OS level, like I'm not going to do that in Fortran, but I never get the joy that I get from Fortran out of these other languages. And maybe that will change. Maybe I'll discover a language that gives me more joy. But so far I haven't. And okay, so back to machine learning. So apparently people are using this, even though Neural Fortran is kind of a very proof of concept, minimal framework. I even call it micro framework. You can only do an arbitrary deep deeply, like densely connected networks. You can do CNNs, although I have been I've been have been talking to a team from NASA, like trying to get some money to develop CNNs in neural Fortran, because they want to use it to apply it in their atmospheric model to speed up some of these parameterization schemes that we talked about earlier.
Mm-hmm.
So nowadays, a lot of machine learning in atmospheric science has to do with replacing more computationally expensive parameterization schemes with a neural net that is pre-trained.
Mm-hmm.
And basically that way they speed up their deterministic simulation code. And for weather prediction, that's important because when you start the model at midnight, the sooner you have the results out, the sooner you can, give the prediction out to your users. And because it's a prediction, it's very timely. Time matters. The sooner you give it to them, the better for them. So there's greater value in it. There's value in speeding up models. There's value in machine learning for atmospheric science. And because all of the atmosphere and ocean models are in Fortran, and nobody's gonna rewrite that anytime soon to other language, people are trying to find ways to put pre-trained machine learning models into deterministic Fortran code. And I believe that's where neural Fortran really comes in, because you can, there's kind of a framework called, I believe it's called the Fortran Bridge that I collaborated on. It's by Jordan Ott and collaborators from UC Irvine. So basically, it's a framework that lets you train in Fortran and use the model in Keras, or train in Keras and use the model in Fortran. So it's kind of like a basically what it says, Fortran Keras Bridge, exactly what it sounds like. So, and that uses neural Fortran as the Fortran piece. So that's really the development that we're going toward in, not necessarily rewriting big code bases from one language to another, but getting the best out of each and applying it where we need it.
This is so interesting. You made me super excited about for using Fortran for machine learning, and maybe I'll give it a spin at some point, building a CNN. Who knows? Maybe I succeed, maybe I don't. But I think there was a super interesting podcast, Milan, and I really much appreciate you sharing so many information with us. Maybe after the podcast we can be in touch via email, and you can send me some links to like books where people can learn about more CFD for meteorology, and we can put that in the description, because I think also using CFD for these kind of weather prediction modeling, for example, topics is super interesting, and maybe people want to learn more about that and became inspired by listening to this podcast. So again, Milan, thank you so much, and to everyone listening, get Milan's book on modern Fortran.
Of course, Yusuf. Thank you so much. I'm very happy for this opportunity and to talk to you. And like Yusuf said, get a book if you want to learn Fortran, and you can email me directly any question you have about it, or if you need help. That's basically kind of like a lifetime customer support. I answer all emails.
I love it, Milan. Thank you so much, and enjoy the rest of your week.
Thank you, Yusuf. You too.